heard that after like 6 or 5.
No, that's me.
Gets a lot of strain.
They don't want to. That's not right.
What are you, 6'6"? You're 6'5".
There's no room to put that pizza, so you're gonna have to put it here. I don't think there's room. I mean, just look at these pathetic, chairs. Hmm? Yeah, but this is like flat.
Yeah.
You have to put it somewhere. Just remember to collect it when you're ready to go.
Not really, actually, it's really fun. I'm like, maybe we just tell her.
I know, you're sure. That's something you can tell, like, not like, I estimate was nice wrong all the time. Most of it really.
Yeah, well, to you, like. Well, no, shit.
Like a lot of it, as a book.
Well, our hit is generally like. So he's like.
All right, so let me look at the time. All right, so it is 5:30. I'm gonna get started. And as the announcement, said, we are, past the point where, I can drop people and you guys cannot even drop yourselves anymore. So in other words, we are stuck at this point. So that means, I'm no longer, going to put a waiting room in Zoom. People can just, come right into the class during the Zoom meeting. It's not a problem. I'm not going to take roll anymore. There's no point in doing so because, I cannot enforce any consequences anymore other than, if people are not absorbing the material, the final exam is not going to look pretty. So we're going to move right on to what we need to talk about today. So there are several things. One is, how do we call a subroutine? How do we return from a subroutine? It sounds like two different topics, but it's really one single matter because it boils down to what is the agreement between the caller and the callee? What can the callee assume that the caller would do? And what does the caller have to do, to set it up so that the callee says, okay, I can find whatever I'm looking for here, okay? So that's the caller-callee agreement, and we'll start with that. And then we'll talk about something that's relatively simple, which is how do we return a value from a subroutine? And we are talking about a scalar return value. Because in C++, as well as in C, you can return what we call a scalar value, which is basically an integer, a float, a double, a pointer. Those are all, scalars. The non-scalars are structure. So you can actually return an entire structure or an entire object as the return value of a subroutine. It is awfully inefficient, and that's why most people do not do it. But as far as the language is concerned, it is supporting it. And then the third thing we're going to talk about today is the concept of parameters. So it is called an argument from the perspective of the caller, and it is called a parameter from the perspective of the callee or the subroutine that is being called. So we'll talk about all of those things. They are all in these particular modules or written modules already. These two look very much the same because I wrote these two on 2 different dates, and I did not realize that I had one already, so I just wrote the other one, not knowing that I got one already. So they should be consistent, just slightly different ways of looking at the same thing. And then the third one we may not be able to get to, which is callee only considerations. That has to do with local variables. Today's lab does not have to do with local variables, so that's not something that we have to get to in today's lecture. All right, so what we'll do is we're going to pick up from where we left off from the previous lab. So let me get back to where we are supposed to be at. I just clicked the wrong button. All right, so in the previous lab, which is stack operations, we actually, you guys have experience, the calling and the calling and returning, part of that subroutine. You guys have to track down how many stack locations were used in the process. And I can see that you guys use different ways of figuring out the answer, which is fine, okay? So what we'll do today is to kind of continue with that topic, and I will go ahead and write a program to illustrate, how we call, how we return, and then we'll go through the trace analyzer so that we have a way to really analyze what is going on the stack, what is being pushed, who's pushing it, and how do we make use of the content that is on the stack. So we'll start with that. And that can be done using just a plain text editor. If you do not want syntax highlighting, you can use Notepad. Okay, any plain text editor will work. If you want syntax highlighting, I do have the syntax highlighting rules that is available for new Vim and also Vim. Vim stands for VI improved, and VI by itself stands for visual, which means in the good old days, there are non-visual editors. They're called line editors, when you edit one line at a time. So when I took assembly language programming, I was only using line editors. Hey, it's better than a teletype terminal, okay, which is printing actually on paper. This one actually has a CRT. So we consider that pretty high tech back in those days. It's like, what do you mean? It is a CRT. It's not a typewriter. Wow, and it has color too. Some of those the CRTs, some of those dumb terminals are also color capable. So those are like super expensive back in those days. All right, so what we'll do is we are going to write some code, and then we'll take a look at how that code operates and how it functions. So we are going to, so I'm using a plain text editor here without highlighting. So we'll say, ff.ttp-asm. So this is resembling the C code that we talked about in the previous lecture, where you have main calling f twice, okay? So we'll have a no-op instruction first. So the no-op instruction has to be here because of a bug in Logisim. So because of a bug in Logisim, you have to start the program with a no-op, but this is only required if you want to run Logisim from the command line, which is really strange. If you run Logisim from the GUI, the graphical user interface, it doesn't need this no-op interface, no-op instruction. So it's just kind of strange that it needs it right here. So we'll jump to main, and main is just going to be a label here to mark the entry point of the main subroutine. In the main subroutine, we're going to, by default, put a halt instruction, to basically represent the return 0, which is basically saying, okay, when main is all done, what are we going to do? There's nowhere to return to. Because in a real environment, in a real computer, when main is done, it is returning to the caller of main, which you cannot see normally. And then that in return will kill the process, which then in return will get you back into the debugger. If you're doing this in code blocks or VS Code, or it will return you back to the command line if you're doing everything on the command line interface. So now the question is, where's F? Well, here's F. So now the question is, how do we call function F? So you might, if you go back to the lecture from the previous class and also the reading module corresponding to the previous class, the way we set up a call is, now don't copy this, don't write this down, okay? Because if you do write this down, you're gonna have a lot of insertion mark and whatnot. So instead, you might want to just jot down the time. It is 5:38. And basically, that's the starting point of the explanation of how to call a subroutine and how a subroutine returns to the caller. So this way, you can quickly locate which part of the video to watch again if you want to watch it again. So we know this has to be somewhere within the instructions to call a subroutine, because after all, we kind of need to continue execution in the subroutine when we call a subroutine. Okay, so we know this has to be there somewhere. But we cannot do this until we help the subroutine to remember where it's supposed to return to. So where it's supposed to return to is the instruction right after the JMPF instruction here. Okay, well, one thing we can do is to use a label to designate where it is supposed to return to. So we'll just say return point 1 here. Okay, so return point 1 right here is, at this point, it is the address of the halt instruction, which means when the subroutine is all done, we'll just continue execution at the halt instruction, and we conclude the execution of the entire program. Are we good so far? All right. So this entire program has to use the stack, because remember, the discussion of the stack was quote unquote a digression, but it's really not a digression. It is more like a prerequisite, because the place where we store the return address is on the stack. Okay, now it is not coincidental that the stack is first in and last in, first out, because the last subroutine that you call has to return to the second last subroutine that you call. So the last in, first out ordering also has to do with the call return sequencing of subroutines. Are we doing okay so far with those concepts? Are we kind of making association between the last in, first out ordering and how subroutines behave in terms of calling and returning? Okay, all right, so we'll move on. So somehow we have to get the label or the value of the label pushed on the stack, because the pushing is the only thing that you can do to add something to the stack, and then popping is referring to removing something from the stack and optionally storing that something that you're removing into a register in this case. So we need to push the label of return point 1 on the stack. So note that we are not pushing the halt instruction, we're pushing the address of the halt instruction. This is what we need to do. So now we kind of try to recall, the sequence of instructions to push something on the stack. The first thing we need to do is to reserve the spot on the stack, which is done by decrementing the stack pointer. The stack pointer is register D, because that is how I have chosen, this is how I have chosen, which register to serve as the stack pointer. So a decrement D will reserve the space, for this content. And then to store to where register D is pointing to is this thing here. And then register A has nothing in it, right? It has an uninitialized value in it. Well, that's okay. We can fix that by saying LDI A with the name of the label. And that would push the return address on the stack. So the lines 9, 10, and 11 collectively is pushing the return address that we currently call return point 1 on the stack. Is that okay so far? Right? Now, since we're using the stack, it probably is a good idea to initialize the stack pointer. In other words, we have to make sure that register D starts with a specific value, which represents that the stack is empty when we start the execution of this program. We know that location 255 is the last location on the stack. But remember, when we initialize the stack pointer, we have to initialize it to 1 byte past the actual end of the stack. So we have to initialize it to 256, which means we are also initializing it to 0, because you cannot represent 256 using only 8 bits. So that means, at the beginning of the program, we can use LDI D0 to initialize the stack pointer, which is normally not really necessary, because everything, all the registers, we set to a value of 0 at the beginning of the simulation anyway. So this is not really needed, but I want to put it here just so that we know how we are supposed to initialize the stack pointer. All right. So this is all we need to do from the caller's perspective. So from the callee's perspective, in this case, F is a void function that does not do a single thing. In other words, the body of the function or the definition of the function is just open brace, close brace. There's nothing to do. So it returns right away. The question is, how is it going to return? So this goes back to the agreement between the caller, which is main in this case, and the callee, which is F in this case. The callee is always going to assume at the entry point of the subroutine, which is where the blinky cursor is at this point, the stack pointer points to the return address. That is a universal assumption for every single program that we are going to talk about in this class. It is also a valid assumption for many architectures and many compilers. So eventually, this convention is not about the architecture, it is about the compiler in terms of what code to generate based on what assumption. Most compilers still make this assumption that at the entry point of a callee, the stack pointer points to the return address. You go like, oh, goody, because I got nothing else to do. So let's just get that return address and use it to return to wherever I'm supposed to return to. Okay, so the LD instruction, it will accomplish this. So we have LD, you can use register A at this point. I'm going to choose another register. It doesn't have to be register A, so I can use register C. So now what I have done is to say, whatever the stack pointer is pointing to, let's put it into register C. But because of the agreement, I know that if the caller is setting up the stack correctly, I'm moving the return address to register C. So that is how I make use of the content on the stack, which means at this point, that content on the stack, that byte on the stack is no longer needed because I have just used it for something. So I don't need it anymore. So incrementing the stack pointer basically deallocates a location on the stack to basically say, yeah, we can reuse this byte later on because I don't need it anymore. So this is the pop operation. Okay, the pop operation involves copying whatever the stack pointer points to a temporary place so that I can use it later, and then also incrementing the stack pointer to indicate that that location is no longer of use to me. Are we still doing okay so far? Are we relating these sequences of code back to what we talked about on Thursday last week? Yes.
Does this mean that we need to use the registers for this? Because we're setting C to the return address and D is the stack pointer. So
that is correct. Okay. So it depends on the architecture as well, and this would be an interesting discussion, is in older architectures, the stack pointer is not known as a general purpose register. A general purpose register gets its name because everything that uses register, you can use a general purpose register with those instructions. So we are talking about add, subtract, compare, and or not, okay, load, store, LDI. Those are all the instructions that can apply to any of the 4 registers. So TTP is what we call a general purpose register architecture because the 4 registers A, B, C, D are completely equal to each other. Okay, whatever you can do with register A, you can do it with the other 3 registers. It makes no difference. In a special register architecture, the registers are no longer universal. Certain instructions only apply to certain registers. So any architecture that has a push instruction or a pop instruction is automatically a special purpose register architecture because they are basically treating the stack pointer as a special register and say, hey, these instructions will modify the stack pointer, but you cannot use any other registers as the stack pointer. The stack pointer is a special register in those particular architectures. TTP does not really make any distinction between the 4 registers. So that means if the compiler so choose and say, I want to use register B as a stack pointer, as long as it is being used consistently, that's okay. There's nothing is wrong with using another register as the stack pointer. Okay, but for this class, we're going to use register D as a convention as the stack pointer. So the next question is, then how are we going to go back to the return address? Because JMPI is not going to work. Because JMPI requires a particular operand here. I'm going to use ADDR here. So the operand ADDR has to be resolvable at assembly time. which means it is fixed. You can say, well, Tech, why don't we just say your return point went over here? Well, it's going to work in this case, but if you have two calls to F, this is not going to work anymore because the two different calls to F will have different return addresses, and this is fixed. You cannot change this. So that means that this method is not going to work. Okay, so if this doesn't work, what is going to work? Well, we actually have an instruction called JMP without the I. So if you look up the opcode table, what do you find when you look up JMP, let's say C in this case? What is column C going to describe when we have JMP C as an instruction, as the mnemonic of the instruction?
PC equals X.
PC equals X, in this case, the register X is C. So in this case, it is the same thing as C, saying PC equals C. So I'm going to write this here and then use comment to let you know, what the RTL is describing this. The RTL is basically saying this. Like, okay, what does that mean? It really just means whatever the RTL description is saying. The program counter is updated based on what register C has. That's all it does. So tell me, what does register C has? What does it have? What is the content of register C at that point? The return address. The return address. So what happens when you put the return address into the program counter? What is the job? What is the one job of the program counter? It points to, it has to do with the fetch cycle, right? So what does the program counter do in the fetch cycle? To grab the next opcode, right? Exactly. So by changing the program counter to the return address, it's going to grab the next opcode at the return address, which is exactly what we wanted to do, right? Because we want to continue execution at the return address. So this is how we accomplish that particular task. So in the program that we saw on last Thursday, there were two calls to F. So now we just have to say, oh, okay, we'll call again. So decrement D, LDIA with return point 2, because there are two return points now. Return point 2 is not defined yet, but I'm going to define it later. We're going to push it on the stack, JMPI to F again. And this is where we define return point 2. So this is the second call to function F. I will refer to line 13 to line 16 as the first call to F, and then line 18 to line 22 as the second call to F. What is the difference? The only difference is where am I supposed to return to? What is the return address? The first call is setting up return point 1 as the return address. The second call is using return point 2 as the point of return or the return address. That's the only difference. What about the called subroutine? Do we change the called subroutine, depending on is it the first call or the second call? Nope. The subroutine behaves exactly the same way in both cases because what the stack pointer points to is changed. Is that okay so far? So this is a very static description of the code. Okay, now if this were a recursive program or recursive subroutine, looking at the static code is not going to give you a whole lot of clue of what is going on when this executes. Okay, in this case, it's not really that bad, even though the subroutine got called twice, it's not recursive. But the best way to visualize what is going on is to use the trace analyzer that is built into the assembler. Okay, you can do this quite by hand. You can also use River Spider to do it. So I'm going to use River Spider because it saves a lot of time, and for instruction purposes, it means a lot. Okay, because we don't have to spend a lot of time just kind of fuzzing with the user interface. So to use that, we just run the submit script, and then you give it where you find the source code. And it will do everything, but pay attention, if you do use the River Spider, you kind of have to kind of make sure that you read the messages, because it is possible that it does not assemble the program, but it will complain and let you know there's some problem with the program and you need to kind of fix the source code first. So you can see that assembler finished, validating object code is good. So object code is referring to what you download as quote unquote the RAM file. That is the object code. So if the object code is good, we're starting the simulator, which is basically just referring to LogicSim running TTP. Simulation finished, which means we got to a halt instruction somehow. And then it is collecting, it has been collecting the trace data the entire time. So now it is submitting the trace data to one of the sheets in the assembler. Trace data uploaded, which means it has done all the uploading, all the importing for you. And now we can go to the analysis sheet just to see as a summary what happened when this program executed. So we'll do that. So to do that, we switch back to the browser. We just go back to the assembler. And the analysis tab is now fully updated. Yep.
How do you, I'm curious, how does it get edited from the command line? How do you edit the document?
Well, the whole thing is open sourced, which means you guys are more than welcome to take a look at the source code. So since you asked that question, I will spend maybe 2 minutes to talk about it. So if you look into the shell script, in River Spider, the so-called turning into, submitting code and uploading stuff really boils down to using, I think, wget to as an HTTP request to a certain URL. Okay. So let me find wget. So wget is a command line web browser. Okay, that's how one way you can describe it. It's a command line web browser. You can give it a URL, and then you can give it some additional switches, so it can handle cookies and other things along with just submitting stuff over to a particular HTTP address. Excuse me. And then on the other side, when you look at the extension of the assembler, when you look into the app scripts here, there are two particular functions that are important. Do post is the most important one. So do post is a callback whenever you submit a HTTP request to the URL associated with this particular assembler. Do post is called. Okay, and then E as a parameter is an object, and that object contains basically all the useful information, including the content of the file that I'm trying to upload to the assembler. And then using GAS or Google App Script, it will decode the content and then use it to populate the sheets accordingly. So the entire thing is completely open source. You guys already have this entire piece. River Spider is available as a zip file. You just download it. Okay, so on Mac and Linux, you just download it, unzip it, and you have to read the README file. There are a few things to set up, but once you're done setting up, you're all good to go. If you are using Windows, I am sorry. But one of the prior students also felt really sorry for people who use Windows. So he ported River Spider to PowerShell. So you still need to install and make sure that you have PowerShell in Windows. But once you have PowerShell, then you can set up basically the same thing and use River Spider in Windows. So you got a few choices if you want to do it. Okay, so now we are getting back to the analysis tab of the trace analyzer. In column 1, we can see what is the location of the opcode that I'm executing. In column F, we can refer to the line number corresponding to that opcode. And then in column G, we can see the entire line corresponding in the source code, including comments. So if you have comments on a particular line, it will also show up in column G. So this gives you an ability to follow the execution of a program. So we start on line 2, then we get to line 3. Line 3 is doing a JMPI to main. We end up on line 11. On line 11, we put a 0 into register D. Column D is basically reporting back which register got updated by a certain instruction. So it's no surprise that register D got a value of 00 in this case. All the values are expressed in hexadecimal or base 16. And then on line 13, we immediately decrease D by 1. So it went from 00 to FF. And then we use an LDI instruction or load immediate instruction to store the value of the label return point 1 into register A. And that's why you see that register A got updated to 0E. So the question is, are we really sure that 0E is the right value? You can always go back to the assemble tab. So in the assemble tab, you look up the definition of return point 1, which is on row 17. And then we just have to look up column W. I have to rehide all of these not important columns. So let me hide all of these things. Oh, okay, that's not what I intended. Give me a second here. All right, let's do it one more time. I'm trying to hide column B all the way up to column B. Right click. I have to choose carefully. There we go. So now it looks like a lot cleaner. So column W, as you recall, is the address corresponding to a particular row. So return point 1 does not have its own address, but the next row does. So this is the address of the decrement D instruction that is right after the definition of the return point 1 label. So that means the trace is reporting it correctly. We are putting 0E as a value into register A when we execute the LDI instruction. So this is just a verification. You don't have to do this when you're doing this, but this is a verification that register A got the right value. Then we store register A to whatever register D is pointing to. Register D had the value of FF. It's being used as an address. So location FF in RAM is now being updated to the content or the value of 0E. Are we still doing okay so far in terms of understanding what we are looking at here and what is the value of the trace analyzer? Because it really spells out all the operations. What are we doing to the registers? How are we changing the content of RAM? Where are we doing this in the execution of the program? They are all here. And this is not like something in a debugger where you have to remember to set up the breakpoints. This is all here, okay? The entire execution of the program is here. So are we doing okay so far? Yes.
So 0E is an address, right? So
0E itself is the address of the instruction that is following the JMPI to F instruction. You can actually see it here because this is the JMPI to F instruction. This instruction is at location 0C. But JMPI or any something instruction with an I as the last letter uses 2 bytes. So that means JMPI is going to use our location 0C as well as 0D. So that means that the address of the instruction following the JMPI F instruction has to be 0E. So there are several ways to kind of verify what 0E is actually meaning. All right, so this is basically pushing the return address on the stack. And then we say, okay, now that we have fulfilled my part of the contract to push the return address on the stack, I can now proceed to continue execution at the subroutine, which is represented by the label F. So then we end up on line 6. If you look up the source code, line 6 or row 6 is corresponding to the label of the subroutine F. So you can see this is row 6. It is indeed the first instruction of the subroutine F. And subroutine F doesn't do a single thing. It just wants to retrieve the return address. The return address is still pointed to by the stack pointer. The stack pointer has not changed after we have decremented it to FF. So now we go to location FF. We retrieve the content at location FF in RAM, which is 0E, and then we put that 0E into register C. This is what LD does. So I would definitely encourage, if you do not know the answer yet, okay, I would encourage that you investigate and find the answer. Compare and contrast CPR register A, register B versus LD register A in parentheses register B. Because when you look at the RTL descriptions, they are very similar. The only difference is there's an extra asterisk in the case of the LD instruction. You also want to look into ST. So in this case, you want to look into ST in parentheses A, comma B, and contrast that to LD AB, because you will find that, oh, they look very similar because in both cases, there's the asterisk. The question is, the asterisk is before which register? So all of those are very important things to do because these three instructions, the ones that I just mentioned, CPR, LD, and ST, they are very different instructions despite they seem to be similar. But the differences is crucial from this point to the end of the semester. So it is important to get that all cleared up as soon as possible. All right, so the next thing we do is to increment register D. Register D had a value of FF. It is now incremented to 0, 0. And then the JMPC instruction, as we commented right here, is just copying whatever is in register C to the program counter. Register C has a value of 0E, and we can see that the next instruction is continuing, we are continuing execution at location 0E. Just as what we described earlier, because I wanted to describe how the return instructions operate. Is that okay so far? So I'm not going to finish describing the entire thing because it's repeating the cycle again, except this time the return address is changed. But the mechanism remains exactly the same. So we do okay so far in terms of how we call a subroutine and how a subroutine return to where it's supposed to go. Yes.
Just a quick question about JMP versus JMPI. The JMPI is supposed to be used for labels. JMP takes register.
Yes. So JMPI does not always have to take a label. It can take anything in the form of a postfix expression. The value of the expression has to be resolvable at assemble time. So that's JMPI. JMP, on the other hand, will take a register as an operand. So the value of the register at the time of the execution of the JMP instruction determines where it is going to go. JMPI, on the other hand, has to go to the location that is quote unquote predetermined at assemble time. So does that answer the question? Okay. Any other questions? That's a very good question. Do you have any more questions at this point? Yep.
One more speed for employee agreement. Can I just take a quick look at it?
All right. So I will say that it is important for us to pre-read the modules at this point because we are at a point where the concepts truly stack on top of each other, no pun intended. Okay, I will put it this way. We'll keep pushing, but there's no popping from this point on. The stack hopefully is not going to overflow at the end of this semester. So you need to make sure there's enough stack space. Hopefully there's no stack overflow.
So this is the caller-callee agreement. It describes basically the same thing that I have just talked about, but it also talks about arguments, which is kind of next. Okay. Is that okay? Now, the very same thing that I just talked about, using the demonstration, that was the whole purpose of the lab last Thursday. And that was why I said, don't try to use the 1,000-monkey approach and just go through that lab slowly and make sure that you understand the content, because it is part of the instruction. Is that okay? All right. All right. Any other questions before we move on? No questions? Okay. So since you don't have a question, but I do see that some people may not be fully understanding the concepts, it is important to review the content of the lecture or your own notes after class, okay, especially at this point of this class, because I'm showing you a lot of stuff. So one thing you can do if you have a computer right now and you can actually get to this page is to make a copy of this. Go to File and then say make a copy to your own drive, because then you have a snapshot of what is the sample program that I was talking about and what is the analysis, what is the trace of the entire program. That will give you the tool to basically go through this again, but this time you can comment line by line, row by row, what is happening, and you can tie these to the result of the execution of this program to the concepts that we just talked about. So now you're associating the outcome of the execution of a program to the concept that the program is supposed to illustrate. Is that okay? Right? Now, in this case, how many stack locations were used during the entire execution of this program? How can we find out? Okay, so how do you know there's only one? Oh, okay. But there's only one, okay? So how one stack location, but how do we know there's only one stack location? We look at column C, right? So we look at column C, which reflects each time we have an entry in column C, it is basically saying one location of RAM got overwritten. So this is telling us the location FF got overwritten with the value of 0E. And then this one here is saying location FF again got overwritten by the value of 14 in hexadecimal. But it's the same location. So if I'm asking you how many locations got overwritten in a stack, the answer is 1. If I ask you how many times that location got overwritten, then it will be twice. Is that okay? Does everybody understand how to make use of the analysis tab of the assembler? If I were sitting on that side, I would probably think this is a critical tool to understand the concepts from here on, because it illustrates exactly what is happening to the registers as well as RAM locations as we execute these programs. Are we good so far? Okay, I want to leave enough time for you guys to respond, because I've been to many Zoom meetings where someone is going to ask, are there any questions? Moving on. 2 seconds. All right. No questions? All right. Okay. So we're going to move on and talk about how to return a value. So I'm going to show you the C code first, and then we'll, oops, okay. So, I forgot that :X does not exit out of a Google Sheets. But it does, getting out of a VI session. Okay, so we're going to look at returning a value now. So we'll just call this return value and put it into the temp folder. And all of these programs I can upload at the end of the class as well. So this way you have the full code that we talk about in class. So we'll talk about the C code first. So I'm going to pound include stdint.h standard integer.h uint_t, just so that we can emulate as much as possible the implementation in assembly code. So the return value is an 8-bit unsigned integer. We'll call this subroutine Johnny, which takes no parameters whatsoever. And the only thing it does is to return a constant value of 5. Do we have any questions about this particular subroutine other than how does Johnny have anything to do with 5?
It's not once.
$5.
$5.
No, this is a movie reference. You guys are way too young, but if you ask your parents or possibly your grandparents, they will tell you, oh yeah, it's coming from the movie called Short Circuit. So in the movie Short Circuit, the robot is called Johnny 5. 5 was the actual destination of the robot, but later on the robot called himself Johnny. And the most famous line of that movie is Johnny 5 is alive. And that's the robot referring to itself and say that I'm alive. Johnny 5 is alive. Well, there's a sequel to that movie, so we know Johnny did not quite die at the end of the movie. All right. So now we want to say, but how is this implemented? Okay. We haven't really talked about how to allocate for local variables. So this is the best we can do. We just call this a routine and we say, let's not do anything about the return value. How many people have done this in your program in CISP310? A particular subroutine is supposed to return a value. You just go like, don't care. Did you guys use printf? Printf has a return value. Did you pay attention to the return value of printf? Probably not. Okay, in most cases we don't. Okay, so this is not like the first program ever to ignore the return value of a program. So I'm going to write this program, and then you guys will identify how a value is returned. Okay. And I will do a vertical split. Okay. And this way I can keep showing the C code while working on the assembly code. So we'll do a return value.ttp-asm. The extension is what is hinting Vim to use what syntax rule to do the highlighting and whatnot. So this is helpful. So once again, start with no up, pi to main. In main, we initialize the stack pointer, and then we put a halt instruction at the end, and then we just have to call Johnny, okay? And Johnny is, well, the same thing. So we decrement D to allocate for a byte to store the return address, LDI return .1, and to be defined later, okay? And we have to put it into a register. And let's use register B here, just to emphasize that you don't have to put it in register A. Register A, B, or C, they're all fine in this case. And then we store the return address to where the stack pointer is pointing to, like so. Continue execution at the subroutine called Johnny, and then define the return .1 at this point. Okay, so are there any questions about the caller of Johnny? Does it resemble what we did with the previous program when we called function f? It's exactly the same, okay? It is exactly the same. The fact that a function returns a value does not change how we call the function. We still have to push the return address, continue execution at the called subroutine. That's all we need to do. So now we try to look at things from the perspective of the called subroutine. So this is from the perspective of Johnny. And we know that the entry point of the subroutine, the stack pointer points to the return address. So we go like, okay, so we are going to do the return sequence. So we'll do a LD instruction. This time we can use register B again. Okay. Or we can use register C, doesn't matter. As long as we use it consistently in the next 2 lines, we'll be fine. So increment D, JMP based on register C. And the only difference in this case is this is what we do. So can someone identify which line is doing the return 5 thing on line 5, coincidentally, of the C code? So which line in the C code, which line in the TTP ASM file is corresponding to line 5 of the return value.c code? This is, I honestly tell you, this is completely coincidental, okay? Line 5 of the assembly code implements line 5 of the C code, which implements the returning of the value of 5. So when people say, give me 5, I say, I can give you multiple. Just coincidental. This is completely coincidental. I did not plan for this to happen at all. But are there any questions? This is all we need to do. So to return a scalar value is based on another agreement between the caller and the callee, which is which register are we going to use to specify the return value? From here on in this class, the convention is we are going to use register A. So register A is the designated register by convention, not by hardware, but by convention to specify the scalar return value. Are we good so far? Yes? Sort of?
So if you're done one time, so register A will do what? Register A will do what? It will designate.
Register A is the designated register to specify the return value of a subroutine. Since we are not going to talk about anything other than scalar, the return value, so we'll just say return value here. So we are going to switch back to the browser just for a moment, because in the browser, there is part of this agreement here. So this part here says if the callee returns a scalar value, the return value is assumed to be in register A. So from the caller's perspective, it can expect the return value in register A. From the callee's perspective, if the callee has a scalar return value, use register A to store the return value. So it's all specified here. Are we doing okay so far? Because I'm just stacking one little thing on top of just regularly calling and returning from a subroutine. So we are now also trying to specify, oh, if you have anything, if you have a value to return, just stash it in register A and that's all we need. We good so far? Okay. So the next thing we're going to do is to ask, well, can we mix and match these things? Okay. Since we have just talked about how to call a subroutine, how to return to the caller, how to specify a return value, what kind of useless program can we possibly write only using those particular elements of a programming language? Now, I call it a programming language because I will bet you all high-level programming languages can do what we just specified. C is, or C or C++ is just one of those many programming languages that have these features. So what we'll do is we look at the program that we are writing, and it's right here, and we'll complicate this program a little bit, okay? So this time, I'm gonna say, okay, let's write another subroutine to return a different value. This time it's called Ryan, which has nothing to do with any students in this class, nor professors of the CIS department. I'll explain that later. And Ryan, as a subroutine, is going to return 7. And of course, you guys are going to ask, what does Ryan have anything to do with the number 7? Now, this question, I think some of you can answer, but since you did not look up the names of actors/actresses, in TV series, you may not know. Does anyone know the association between the number 7 and the name, in this case, last name, Ryan? 7 is referring to the character 7 of 9. And Ryan is the last name of Jeri Ryan, which is the name of the actress who played 7 of 9. And from your perspective, from this generation that I'm looking at right now, you should be referring to the TV series on, I think this one is on Amazon Prime. It is Picard. Paramount, yeah, but it's also available through Amazon, but it's Paramount, yes, that is correct. Paramount Plus, because you have to pay for it. Yeah, so that's why Jeri Ryan, Ryan is associated with 7. When I was a software engineer as the lead of the group of a small company in the software engineering department, my designation was 1 of 7. That's how I ran my software engineering department, was really kind of board-ish. It's a flat structure, I'm not the leader, I'm not the queen of the collective. It's just like, okay, we got things to do, who wants to do which part? And then we just ended up doing everything. It was really nice. It's just really smooth.
It's also director.
Director?
Yeah, director of engineers.
That was my official title. My boss wanted me to sound more important than I was ever.
Okay, so
CIO. Well, from my perspective, it was just lackey.
that's management.
So we do the same thing, okay? So we can use register B here. I mean, there's no need to stick with register C. So you can see how the syntax highlighter is really helpful, because if I specify LDI, it knows it should not be expecting something in parentheses as the second operand. So the highlighting is helping me to debug the program as I go. So it's really helpful. All right, so let's go fix that. It should be LDBD, like so. And then we do an increment D and then JMP, in this case, not C anymore, because whatever register we use to store the return address is whatever we need to use here. So JMPB is what we need here. That's right. So we good here? All right. Yep.
Are you using register B for other stuff or not? Because
Oh, okay, so here's another thing that we need to know about the contract between the caller and the callee. So let's go back to the contract between the caller and the callee. From the caller's perspective, over the duration of a call, the values of registers A, B, and C are not assumed preserved. In other words, as soon as you call a subroutine, you can expect registers A, B, and C all in a chain. Now, they may not, right? But you cannot count on those 3 registers being preserved. Is that okay? So all 3 registers are now available to the callee to use whenever it needs to. So from the callee's perspective, there is no need to preserve the values of registers A, B, or C. Register A is special. You don't have to preserve it, but it is used to return a value. So it does have that one extra row if the callee is supposed to return a value. But otherwise, there's no need to preserve anything, of the 3 registers. Yep.
Since it doesn't act, there's actually like, because in C++ you just specify something as like a void function or int function or something to return a value or not. But in this, you don't really specify if it's returning or not. It's just how
That's
you
correct.
use register A.
Yep. That is indeed correct. Yep.
A value is returned within register A.
That is correct. So in C, if you forget to return, use a return statement that returns a specific value, but the prototype of the function does specify it returns a value, what is going to happen? So the program will compile, okay, unless you turn on all the warnings, the program will compile. If you specify a function to have a return type, but you forget to specify the actual return value, it will compile. The compiler is basically saying, well, since you're a C programmer, you know what you're doing, so I will let you do this, which 99.9% of the time is an incorrect assumption. So the question is, then what is going to happen, right? I did not specify a return value, but the caller is going to say, I'm going to grab a return value as if there's one, and I'm going to do this and that with a return value. So what is going to happen?
Gonna initialize the value, set the value, but it'll just run the function.
It will just use whatever is in register A as if it is the intended return value, even though there's none. So that means it's just going to grab some garbage from whatever register is designated as the return value register and just assume that it is meaningful. That's what's going to happen in C or C++ code if you ever write a subroutine that has a return value type, but you forget to specify an actual return value. Yes?
This may be backtracking a bit, but I'm still having a little trouble understanding the difference between the LD and the ST.
All right, well, I won't spend too much time on it, but I will spend some time to kind of point out where you need to kind of go to investigate, and also how to do a deeper investigation if that is needed. So the instructions that we were talking about is the ST instruction, the LD instruction, and the CPR instruction. Where is it? Let me see if I can scroll. It's higher. Yeah, I can see it. Yeah, so I'm trying to show all 3 lines at the same time. Yep, okay, there we go. Where's my column? Oh, okay, I scrolled already. So my bad. There we go. So when you look at column C, one says x equals y, one says x equals asterisk y, and then one says asterisk y equals x. What is the difference? Where the asterisk is, whether there's an asterisk and where the asterisk is. Asterisk is the reference. So that means in the case of LD and also ST, we are not using register Y to update X. We're using whatever location in RAM the register Y is pointing to update X. So there's a dereference involved in the process, but it's on the right-hand side in this case. When we look at ST, we are not storing the value of register X to register Y. Register Y is not changed. What it points to in RAM is changed. So these are the differences between the 3 instructions. One is directly just copying from a register to another register. One is using the content that a register points to update a register. They can be the same register, by the way. So X and Y can refer to the same register. And then another one, the last one, is updating where in RAM a register is pointing to. So it's not updating register, it's updating where it points to in RAM. Now, this is a very surface level description. The RTL is a high level description of what an instruction does. Okay, it describes the what, but not so much the how. The how is dictated by the microcode in the ROM in the processor. So the best way to really understand the differentiation between these 3 instructions is really to use one of the specific opcode, get to the execute phase of that opcode, and look at the multiplexers, the tunnels, and all of that to establish what component is connected to which other component and what really is getting updated. So that would be the best way to truly understand these 3 instructions. But from this point onward, if you understand what column C is representing with the RTL representation, it would be sufficient. But personally, I would get to the process of architecture to really see how a register connects to the address port of RAM, and therefore controlling which location of RAM we are dealing with, and whether RAM is being read or overwritten, and which other register is involved in the process to connect to the D port of RAM. So I personally would do that. It is my recommendation, but then it is not my grade that you're going to get at the end of the semester. Yes, I did say it in a very pointy way. Just so that people are just listening to it, it's like, oh, tech doesn't mean it. No, no, I actually meant it. As serious as ever. But it is important, okay? I cannot overemphasize, but that's all what I can do. What you decide to do is up to you. Yes.
So if it's stored in reference to this within there's Y and one
It is always pointing to something. A register is only 8 bit wide, which means it can only be.
what it's pointing to has an address.
Okay, the range of value of the register is 0 to 255. We only have locations from 0 to 255. So you can always use a register as if it is an address. The question is, should you? That depends on the context. That depends on whether the register actually has the address of something that is valid. So there's nothing wrong with the instruction. It's only a matter of, are you sure that register Y has the address? And are you sure that you intend to overwrite that location? Those are the only questions that you need to ask for storage. Yes.
So for register A, you said that holds return value, assuming there is a return value.
Yeah.
What about parameters? If we want to pass a number into a function, we need a different register.
We'll talk about that. Yeah, those are all done on the stack. All right, so we are going to get back into this whole program here, and we're going to use yet another subroutine. I cannot remember what I usually use in this case. What is usually associated with the number 12? I'll just spell it out. I cannot remember. So 12 is just 12. So instead of doing this, I'm going to do something like this. Johnny plus Ryan. Which is really funny because this looks like the marriage between a robot and a board. See what will happen. I'm not sure what's going to happen. Something is going to short circuit. All right, so we want to look at this and go like, well, are we really sure that we know how to deal with this? Well, let's check, okay? Checklist. Do we know how to call a subroutine? Yes. Do we know how to return from a subroutine? Yes, we have done this many times already, just today. Do we know how to specify a return value? Yes. Do we know how to get back to the return value? Yes, it is just in register A. Just do something with register A. So in theory, we know how to do this already. So the question is, in practice, how do we do this? So you will now see that it is not quite as simple as it seems. So 12 is the entry point. So in this case, this is how I usually program is I would specify the end code first, just so that I don't forget it. Okay. So I always just implement the return code before I specify the rest of the program. Then I backfill what the program is supposed to do. So the first thing we need to do is, well, it seems unavoidable that we're going to have to call Johnny. Okay, we know how to do that. Decrement the stack pointer, reserve a byte on the stack, LDI register A with whatever the return point is supposed to be. We'll just call this 12_1. Store that to where the stack pointer is pointing to. Oops, I just moved my mouse pointer. And then JMPI to, in this case, we call Johnny first. Johnny, there we go. All right. And this is where 12 underscore 1 is. Okay. Do we have any questions about how we just called Johnny as a subroutine? Not a problem, right? I mean, this is exactly what we have been talking about, calling a subroutine with no arguments whatsoever. All right, so we're gonna have to call Brian again. So we have to decrement D, LDIA with 12 underscore 2, which is the second return point in this entire caller. You'll push it on the stack, JMBI to Ryan, and then we specify the label representing where it should return to over here. Well, we have two calls, and the problem is they both want to use register A to store the return value. So that means right on line 22, we have the return value of Johnny, which is 5, in register A. But it's going to be overwritten by the time you call Ryan. In fact, it's going to be overwritten when we get to line 24. And go like, we have to stash it in some other register, right? The most immediate thought is we can just stash it in, register C. Can you really trust register C not being overwritten by Ryan? The answer is no. Even though we can see the code of Ryan and say, see, Ryan is not going to overwrite register C. But that's not part of the agreement. The agreement is it is free. Ryan is free to overwrite any of the 3 registers, A, B, or C. Okay, so Ryan may not be using it right now, but Ryan can use it later. So I cannot count on it. You go like, dang it. So where am I going to put it? Where do you think we should put it?
Are we gonna shove it into Van?
You guys are both correct. Yes, go ahead. On the stack, exactly. So if we cannot stash in the register because everybody wants to do something with the registers, we'll just stash it on the stack. So we will push it on the stack. So right here, we're going to push the return value of Johnny on the stack. So that's a decrement D. We don't have to store anything in register A because it's already the return value of Ryan. So we just say STDA. In other words, we just pushed the return value of Johnny on the stack. So now that this thing is on the stack, hey, we're not worried anymore. So right here at this point, okay, register A has the return value of Ryan. And then we are going to say, we somehow need to get back the return value of Johnny so we can add those things together. So what is the opposite of push? Pop. And how do we pop? It is exactly the opposite of push in every way imaginable. Okay, so in push, we decrement first. So in pop, we increment as the second thing that we do. In push, we store as the second operation. So in pop, we use LD as the first operation or load as the first operation. So we now put it into register B, like so. So at this point, register B is going to contain the return value of Johnny. Cannot type, there we go. So now we have the return value of Ryan in register A, we have the return value of Johnny in register B. You just have to add those two together. So I have a choice again. I can say add BA, or I can say add AB. Which one should I use? Remember what 12 is supposed to do. Add AB, because otherwise I have to put register B back into register A, because register A is supposed to be the return value. So add AB will get both two things done at the same time. I'm adding the return value of Ryan and Johnny, but I'm also at the same time putting that return value into the right register, which is register A. Are we good so far? So we're going to change the program just a little bit here. So instead of calling Johnny, we're going to have some fun, and we're going to call 12. Okay, so that means by the time we get to the halt instruction, register A should have the value of 12, which should be reported as 0C because it's going to be in hexadecimal. All right, so we'll give this a try, okay? And see what happens. Okay, so we're going to submit return value.ttp ASM. Taking a little bit longer this time. Hmm?
You got a bit more code.
Well, it's not that much more. There we go. I think it's just Google, thinking. Are you guys using a Google Sheet as an assembler? That's not a proper use of a spreadsheet. But at the same time, it doesn't say that we cannot use it as an assembler. All right, so you actually just saw how the analysis tab got updated because there's actually a lot of stuff happening. And if you're kind of impatient and just wanted to say, did it work? Then we can just go all the way to the end and then we ask, what was the last thing we put into register A? It is 0C, it is correct. The register D gets back to where it's supposed to be, which is the original value, 00. Yes. So for everything, from everything I can tell, this program worked just fine. So what is the value of this program to you? It has to do with how you track the use of the stack. Because in this particular case, we are not only using the stack to store the return address, we're also using the stack as a place where, I kind of need to save this particular value, but I have nowhere else to put it because I cannot trust the registers. I can just push it on the stack. And then later on, when we need that value back, we just say, okay, I can just reach to the stack and say pop, get the value back, and now we can continue the processing. Yes?
I think you may have already said this, but are you gonna post these things as an announcement so we can like take a look at the code?
Yeah.
All right, excellent.
Yep. All right, so we only got 5 minutes left or 4 minutes left. The last concept that we kind of need to understand, but there's not enough time, but the lab does have instructions for that too, is how do we pass parameters, pass arguments to a subroutine. So for that part, from the caller side, if there are arguments are pushed in reverse order. What does that mean? It means the last argument is pushed first. Is that okay? So if the arguments goes like 1, 2, 3, comma separated, then 3 is pushed first, 2 is pushed second, and 1 is pushed last. Okay? And as a result, the last argument has the highest address because when we push, we are decrementing the stack candidate. So whatever you push first has the highest address. And that is done before the return address is pushed. Is that okay? So from the callee's perspective, at the entry point of the callee, the stack pointer is still pointing to the return address because it's the last thing that we push on the stack. But do you think we know where to find the arguments in this case? So to understand this part, it is helpful to draw a picture about the stack. So let me use a spreadsheet program to illustrate. Okay. So let's just say that we are calling a subroutine with 1, 2, 3 as the arguments. And then on this side, we're going to look at what is happening on the stack. So we can see that 3 is going to be pushed first, 2 is going to push second, 1 is going to push last, and then followed by the return address. So there are 4 bytes being used on the stack just for this particular call. When the subroutine gets control, when we're at the entry point of the subroutine, this is where register D is pointing to. So register D is always arrow D pointing to the return address. So do you think we can get back to the parameters that were pushed earlier as arguments by the caller? Sorry? Well, sure we can. Because we know where the stack pointer is, right? The stack pointer is register D and is known to every single subroutine. So we can now say, we are not supposed to change the stack pointer because you'll remember the gremlin problem. So if you increment the stack pointer, whatever it was pointing to before can be lost, and we don't want that to happen. But we can use CPR. So we can copy the stack pointer D to register A, B, or C. Take your pick, right? So now we can make a copy. So we can say, we can say the register C now has the same thing as register D, which both are pointing to the return address. So from here, if I want to get back to the second parameter, what do I do?
You just pretend that register C is register D, and then you increment it twice to get back to the second.
Exactly. So if I increment register C once, it gets here. If I increment it one more time, it points to this location. So a single LD instruction using register C will retrieve, in this case, the second argument. And that's how it works, okay? The caller and the callee are, agreement is basically just specifying, if you got arguments, push the arguments first, last argument first. And then the very last thing to push is the return address. Then you continue execution at the entry point of the subroutine. The subroutine is guaranteed to have the stack pointers pointing to the return address. And any parameters will be at location higher than the return address. Now, can there be a misunderstanding between the caller and the callee in assembly language code? The answer is yes. Okay, so with a subroutine that has 3 arguments, you can mistakenly only push 2 things on it. But then the third argument or the third parameter will be assumed to be at a location that is not really the third argument or third parameter. But that's not the fault of the system, it is the fault of the program. In C++, you cannot do this because the compiler checks, okay, to make sure that you're pushing the right number of things and those things are of the right type. So in assembly language programming, there's no such thing to help you to get rid of those problems. All right, so I will give you the access code to the lab because you will need that for the lab. So I will upload and use the announcement to send you the source code that I work on today. By the time we get to the lab, I promise I will not delete those files. So in this case, we have the lab called params and return value. And then the access code is frame. I'll explain why it's called frame on Thursday. The frame, all lowercase, is the access code.
Like, how do you?
Oh, okay, I have not checked that thing for a long time.
I was wondering, is your throat okay?
Huh?
Is your throat okay?
Well, it's a little dry. I don't know exactly what.
Okay, I have this cough thing, but it's.
I think I'm good for now, but thank
Okay,
you.
good.